All right, the last reaction we have to cover for chapter 20 is a new oxidation reaction that's quite versatile called the Baeyer-Villiger oxidation. And let's look at the overall reaction and then we'll see it applied in a few different contexts. The overall reaction involves a ketone or an aldehyde, it doesn't really matter. And what you do is you react it with a peroxy acid. Does anybody remember a common example of a peroxy acid we've seen before? Give you a hint, think of epoxides. How do you make an epoxide? MCPBA is a peroxy acid. So something like MCPBA could be used in this example. And the neat thing with this reaction is it will end up inserting an oxygen between the carbon and the other carbon coming off the end. So you end up with an inserted oxygen. And there's a couple different ways you can do this. Let's take a look at an aldehyde. Just a really simple aldehyde. If you treat this with a peroxy acid, the question then becomes, where is the oxygen going to go? Is it going to go on the left in between the two carbons, or is it going to go on the right in between the carbon and the hydrogen? And experimentally, we know it inserts in between the carbon and the hydrogen, which means you can actually convert an aldehyde to a carboxylic acid. The only way we knew of doing this before was to reduce an aldehyde to an alcohol and then re-oxidize it using a chromium-based reagent. This is nice because it's one step, it avoids chromium, it's really easy to do. All right, if you do a ketone, you get something different. We'll do a symmetric ketone this time. Instead of that, you end up going from a ketone to an ester. In this situation, though, because the ketone's symmetric, it doesn't matter which side the oxygen gets inserted into because they're identical products, right? So it doesn't really matter. We're going to talk about what happens with unsymmetric ketones later. There's actually a trend that is helpful to memorize, but let's first cover the mechanism before we do that. All right. We'll just do a ketone as our example, although the mechanism is very similar with aldehydes. Just swap out one of those carbons for a hydrogen. Actually, sorry, I'm going to draw all these bonds here. So that's our peroxy acid. And in the first step, the oxygen furthest away from the carbonyl is going to attack in and kick up electrons. And you end up with this highly charged intermediate. In the next step, we're going to do a proton transfer and move the proton from the charged oxygen over to the carbonyl oxygen. So this can actually be done intramolecularly because the ring strain's not too bad. At least that's how the book shows it. So now that proton's on the next door oxygen, got shuttled over. And then the next step's the goofiest one. And bear with me. This lone pair is going to clamp down. And then instead of kicking off the oxygen, you're actually going to observe an alkyl shift. So this entire alkyl group circled in green is going to shift over, whoops, let me keep it red, to this oxygen. It's actually just going to hop one atom over. And then on the remaining portion, this bond is going to break, form over here, and then kick down electrons onto that oxygen. So it's one of the most complicated mechanisms we've seen to date because it involves an alkyl shift. All right, so now let's think about the different pieces, right? So I'm going to highlight it. We've got this blue piece right here, right? So let's draw what we get with that. And I'll actually color code it with blue. We've got that carbon-oxygen double bond with a methyl group that's still coming off of it. We have a single bond to oxygen. And then that methyl group that slid over is now coming off of that oxygen, and so I'll just circle it to show that it shifted over to that oxygen. Does that make sense? Okay, let's do the other one. I'm going to add a pen color, actually. We'll do the orange half now. Okay, so for the orange half of the molecule, we're forming a double bond right there, right? The R group is still coming off that same relative position. And then down here, we now have an OH group. Usually what happens is this is your desired product, the ester. And then the carboxylic acid in orange on the right is going to be your byproduct. So I'm just going to circle this and say carboxylic acid byproduct. And typically it's pretty easy to remove that carboxylic acid byproduct because all you need to do is aqueous extraction with a weak base. That deprotonates your carboxylic acid. It'll go into your aqueous layer. Just do a simple extraction with an organic solvent and you can isolate your product. Way better than using a chromium-based reagent. Infinitely better. So a lot of chemists really like using this reaction. Does that make sense? Yeah, this is the Baeyer-Villiger oxidation. The name, in terms of the spelling, is at the very top here. Baeyer-Villiger. And I will test you on spelling. I'm kidding.
Like PCC or...
No, this reagent commonly is just peroxyacetic acid, where R is a methyl group. That one's very common. You can use MCPBA, but it's not necessary. So peroxyacetic acid is very common. All right. So now we need to look at that green circled area. So I talked about that alkyl shift, how one of those groups slides over onto that oxygen. There's actually an important order of priority. So let's write that down here. So shift priority. Hydrogen is clearly the best. So you saw with aldehydes, the oxygen always inserted between the hydrogen and that carbonyl carbon. That is always going to be number one. And then next highest is if you've got a tertiary carbon. And then next highest would be a secondary carbon. And then next highest you would anticipate being a primary carbon, but it's not. Experimentally, we know that phenyl groups tend to shift. They don't shift as well as a tertiary or secondary carbon. And then last but not least, we've got primary, and the worst one is a methyl group. So this is the shift priority for where the oxygen wants to go for these alkyl shifts. I'll show you a cool example of this in action. Oh, methyl. All right, so let's take an example. So we've got a cyclic ketone. And if you treat this with RCO3H, that's just the condensed version of a peroxy acid, you're going to end up inserting an oxygen, right? So the oxygen in this case, does it have a preference where it wants to go? It's symmetric, right? So we're going to insert an oxygen. We're not reducing the number of carbons, so this oxygen is actually going to expand the ring size to a 6-membered ring rather than a 5-membered ring. And you can get an oxygen up here. This is a cyclic ester. And a cyclic ester is also known as a lactone. Lactones are common in the pharmaceutical industry. They're common in biochemistry. And there's a lot you can do with this now, right? If we think about our ketone, could we break open that ring system? Was there any way to break open this ring system before? No, we could add Grignards to it and add carbons to it, but we couldn't split the ring open. By doing this, now all of a sudden, if you add a Grignard in, you can actually ring open it. If you treat it with a reducing agent like LAH, you can ring open it. So this allows you to ring open functional groups that previously we were unable to ring open. So it is kind of neat in that regard. All right, let's see a few more practice problems. Did you say you don't understand? Yeah, let's try this, right? So LAH for step 1. Step 2, right? LAH we know can reduce an ester. Okay, so if you reduce this, what you're going to get out is going to be an alcohol up here. And then down here, everything's going to stay put, and you're going to get an alcohol like that. So you can actually ring open this into a diol now, right? It's kind of neat. Alternatively, what you could do is treat this with, let's say, methyl magnesium bromide. Sorry, this is a little cramped. Followed by an acidic workup or just workup with water. And now if you do this, right, you get an alcohol. You get 2 methyl groups adding in because we know it adds in uncontrollably. And then your other alcohol is just going to dangle off over here. So you can actually ring open these into diols pretty easily. It's kind of a clever workaround if you are stuck with the cyclic ketone. Does that make sense? Yeah. Feel free to interrupt me if there's something that doesn't make sense. If you have a question, chances are other people do too. All right. Let's try to predict the products for these reactions. Let's try problem 1. So if we think about shift priority, we've got this hydrogen on the right, and then over here, we've got a primary carbon. Which one's more likely to do the shifting? The hydrogen, right? Which means immediately we know the oxygen's going to insert there with the orange arrow. So again, we can, without even drawing the mechanism, draw it out and say the oxygen has to insert in between the carbonyl carbon and the hydrogen. That makes sense? All right, now the next one, we'd look at this hydrogen and then we'd say, all right, a hydrogen versus a secondary carbon. Where's the oxygen going to go? Hydrogen. So again, we can do that. Let's do one last one for good measure. So this time we've got an isopropyl group on one side and a methyl group on the other. We need to predict which side the oxygen will get inserted into. So let's label these. This carbon we know is primary, or actually methyl, excuse me. Then over here, we've got a secondary carbon. So is it going to insert on the left or the right-hand side? Left. Okay, so if we go ahead and we draw this, we can say, all right, it's going to insert there, give us that. We are not going to get any of the other product where it's like this. This is not seen. Does that make sense? All right, that's the last reaction for the chapter. I know there were a lot of reactions that we covered. At the end of the chapter in the textbook, you can see these reaction maps for all the new reactions we've covered. It's pretty dense. What I like doing is printing off this fill-in-the-blank study guide, and you can tell I took all the reagents away. Print out a few copies of these, just do it over and over and over again. Make sure the ones where we covered the mechanism, you do feel comfortable doing the mechanism as well. People have asked me which mechanisms we need to know. Any mechanism that we covered in lecture is fair game. The ones that we skipped over or glossed over are not going to be on the exam. The Baeyer-Villiger oxidation, I will just flat out tell you, because it's such a goofy mechanism, I won't test you on the mechanism, but I do want you to be able to anticipate the products. I just showed you the mechanism so you wouldn't be just trusting me on blind faith. Make sense? All right, so for the remaining class period, I've got the Chapter 20 practice problem handout up front. Some of those are really challenging. It gets more challenging as you go to the back page, so don't get alarmed if you get to the back page and you can't figure them out. That's just for students that really, really want to push themselves, but try to see if you can get through the first few pages. Tomorrow, what we'll do is go through the practice exam after class, and we'll do synthesis activity in class. So depending on your schedule, you can try to make both. If you can't make the exam review, I'll just record it and put it online. Sound good? All right.